Imagine a character in a simple video game who can only move in two ways. They can jump diagonally up, or they can fall diagonally down. They're always moving forward, one step at a time. On this grid, we can track that movement exactly. If our character takes exactly 6 steps, starting on the ground and finishing on the ground, we can start to see a specific shape. The question is, how many different ways can they arrange those 6 steps to get to that same finish line? This is the core of a field called combinatorics, the study of every possible arrangement within a system. For 6 steps, you could just draw them all out and count them. But when a game, or a real-world system, involves thousands of steps, we need a mathematical shortcut to find the answer. Now let's add a rule. Our character is standing on a platform, and everything below that starting line is a lava floor. If they ever drop below the starting height, they're out. Mathematically, we've just added a boundary. We are now only interested in paths that never cross below that 0 line. Any sequence that dips into the negative numbers is now bad. By filtering those out, we are left with a much smaller, more specific set of safe paths. These are known as Dyck paths. It's a simple name for a powerful idea that even a single rule can turn a random walk into a highly structured mathematical pattern. To count these safe paths without drawing every single one, we use a clever geometric trick called Andre's reflection argument. The strategy is simple. Instead of trying to find the good paths, it's actually easier to calculate every possible path and then subtract the ones that hit the lava. We can identify a bad path by looking for the very first time it touches the forbidden zone. At that exact moment, we flip the entire first half of the path upside down. It sounds strange, but this creates a perfect mirror image of the failure. This mirror mouth gives us a way to perfectly track and subtract every single path that touched the lava. What's left over are the Catalan numbers. This specific sequence of numbers is famous because it keeps showing up in nature whenever things need to be organized without overlapping. It's a reminder that we can use simple geometry to solve problems that would take a lifetime to count by hand. We can make this model even more realistic by giving our character more options. What if they could also take a flat step, a dash that moves them forward without changing their height? On our grid, these show up as flat plateaus between peaks and valleys. Including these level steps create Motzkin paths. If we allow that flat step to cover twice as much ground, we get a stretched out version called Schröder paths. And if we remove the lava floor entirely, allowing the character to move in any forward or diagonal direction without restriction, we find the Delannoy paths. Each of these names just describes a different way that objects can move through a grid when you change the rules of the game. But there's a problem. When we try to calculate these paths for millions of steps, even our subtraction tricks start to get overwhelmed. To handle that kind of scale, mathematicians use a tool called a generating function. Think of this like a zip file for numbers. It lets us compress an endless list of path combinations into a single compact formula. Instead of counting, we just plug our path length into this formula, and it instantly hands us the answer. It's a powerful way to turn the absolute chaos of infinite possibilities into a single predictable piece of data. This might feel like a game, but these safe path rules are actually the logic behind how the real world is built. This grid shows how an RNA molecule folds itself. The math's lava floor prevents it from folding back into a tangled mess. Computer scientists use this same logic for parsed trees, ensuring computers read code in a safe order without crashing. These path rules aren't just abstract ideas. They are the templates that keep our biology and our technology functioning. If we imagine our character taking billions of tiny jumps every second, those jagged diagonal lines start to look like a smooth, continuous wiggle. This is known as Brownian motion, the random drifting movement of particles as they collide with molecules in a fluid. Because we understand the grid math of those individual jumps, we can use it to calculate exactly where a drifting particle is likely to end up. It's the bridge that lets us move from a simple 2D game to the complex movements of atoms. In the end, these lattice paths show us that math is more than just a way to count steps. It's a shared logic that connects the way a game character moves to the very way our world is put together.